Good morning. Myself is Shahina KM, working as an assistant professor in Computer Science Department, Amal College of Advanced Studies. Today, I would like to take a session on functional dependencies in DBMS. What is functional dependency? Functional dependency is a constraint that specifies the relationship between two sets of attributes, where one set can accurately determine the value of other sets, which is denoted as X determines Y. X determines Y, where Y is functionally dependent on attribute of X. That means for a particular value of X, we will get a particular value of Y. Here, X is called determinant and Y is called the dependent. Here we have a table having 4 attributes or 4 columns: roll number, name, and department building. Here we can define a functional dependency on roll number gives name value. Okay, roll number gives name. That means here roll number is determinant and name is dependent. That means here we have roll number 42, 43, 44 and name ABC, PQR, XYZ. For a particular value of roll number, we will get a unique name. Here for 42, we will get ABC, and 43, we will get PQR. That means here 43 is determinant which determines the value of dependent. Here 43 determines that the name is PQR and 42 determines that the name is ABC, and this is a valid functional dependency. Next we can consider another invalid dependency. Name gives department name. Consider the attribute name and department name. For a particular for ABC belongs to the CS department. At the same time, another name ABC may have belonged to IT department. That means the value ABC does not gives CS, which may be IT. If we have another value 45, ABC, he belongs to IT. Then the name ABC gives two values, CS and IT. That means which does not determine the value of department name. Next is rules of functional dependencies. We have 3 main rules. First one, reflexive rule, and augmentation rule and transitivity rule. Reflexive rule means if X is a set of attribute and Y is another set of attribute, then if Y is a subset of X, then that relation holds a functional dependency X gives Y. For example, employee name, employee ID. This is X, and we will have another set Y, employee name. Here Y is a subset of X. That means employee name belongs to X. So we can say that this relation holds a functional dependency employee name, employee ID gives employee name. This is known as reflexive rule. Next one is augmentation rule. When a relation holds X functionally depends Y, then Z is another attribute set, then we can say that ZX gives ZY. That means adding attribute which do not change the basic dependencies. That means we have 2 subsets X and Y, and X functionally determines Y. Then if we add another set of attributes Z to both X and Y, ZX and yz will give another functional dependency. Okay, the same relation holds zx gives zy. Then next one, transitive rule. Transitive rule means if we have two functional dependencies, x gives y and y gives z. X gives y and y gives z. That means x gives y and same y gives z. From this we can inference another functional dependency, x gives z. Okay. X gives y gives z, which implies x gives z. This is known as transitivity rule. Okay. Then next we have some additional rules on functional dependency. Union rule, decomposition rule and pseudo-transitive rule. Union rule means we are combining two functional dependencies. We have two functional dependencies, x gives y and x gives z. Here both cases the left side contains the attribute x and the right side is different. So we can combine these two by applying x gives yz. This is known as union rule. If a relation holds two functional dependencies like x gives y and x gives z, then we can combine these two into x gives yz. This is known as union rule. Next one is decomposition rule. Decomposition rule is just reverse of union rule. That means we have one relation we have one relation having the functional dependency x gives yz. That means x gives yz. Then we can divide or we can decompose the relation of functional dependency x gives yz into two parts. That is x gives y and x gives z. Implies x gives y and x gives z. Next one is pseudo-transitive rule. In pseudo-transitive rule, if x determines y and yz determines w, then xz determines w. That means we have two functional dependencies, x determines y and yz determines w. Here we can check transitive rule. If x gives y and here if y gives w, we can write as x gives w. But here in the second side we will have an additional attribute z. And if we are applying the same attribute into the first side, we will get like this. X z gives yz and yz gives w. We will get xz gives w. This is known as pseudo-transitive rule. Next topic is types of functional dependencies. We have mainly 5 types of functional dependency. First one, trivial functional dependency, non-trivial functional dependency, multi-value dependency, transitive dependency, and finally fully and partial functional dependency. First one, trivial functional dependency or reflexive rule. Here for a functional dependency, A functionally determines B is said to be trivial if B is a subset of A. Okay, A determines B has a trivial functional dependency if B is a subset of A. Same as of reflexive rule. Okay, next one is non-trivial functional dependency. A functionally determines B has a non-trivial functional dependency if B is not a proper subset of A. Okay, that means A gives functionally dependence B is known as trivial if B is a subset of A. Otherwise, it is known as non-trivial functional dependency. When A intersection B, if A and B, if B is not a subset of A, then A intersection B, we will get null. Okay, that case is known as non-trivial functional dependency. Next one, multi-value dependency. For a dependency, A gives B. If for a single value of A, multiple value of B exists, then we can say that there exists a multi-value dependency. For a functional dependency, A gives B. If B gives multiple values for the determinant A, then we can say that there exists a multiple or multi-value dependency. For a multi-value dependency, we have two more rules. A table should have at least 3 columns for it to have a multi-value dependency. For a multi-value dependency, there should be at least 3 columns. And for a relation R of ABC, if there is a multi-value dependency between A and B, if there exists a multi-value dependency between A and B, then there will not be any relation between B and C. It's a rule. We can consider an example. Here we will have a table having 3 columns: student ID, course, hobby. For the student ID 1, we will have a course value science. For the same student ID 1, we will have another course value maths. That means for a single A value, we will get 2 B values. For A gives B, if there exist more than 1 values for B for a single A, then we can say that there exists a multi-value dependency. In this example, here for the single value of 1, here both case the value of A is 1. Then here in the course side, here we have 2 different values, science and maths. That means we will have multi-value dependency. By using this, we can derive another table as student ID in all these cases is 1, science, cricket, because here for the science table, the hobby is cricket. Then for the next value, for the next one, we will have maths and the hobby is different, hockey. So we can combine all this like this: 1 science, hobby, then for 1 maths, hockey, then 1 science, we will have the next hobby, hockey. Okay, we will get multiple values. So this will lead to normalization. Next one is transitive dependency. We already discussed transitive dependency. If a relation holds 2 dependencies, A gives B and B gives Y, then the same relation holds another indirect dependency known as transitive dependency. A gives Y. Okay, this is known as transitive dependency. To achieve third normal form, we have to eliminate transitive dependency. Next one is fully functional dependency. Fully functional dependency means if it is a functionally dependent on that attribute and not on any of its proper subset. That means the dependent should depend the complete determinant, not a part of determinant. For example, here we will have a table having 4 attributes: employee ID, project ID, days and project cost. Here we are defining a functional dependency: employee ID, project ID gives days. That means if we get an employee ID of an employee and project ID, then we can calculate the number of days required for that particular project for that particular employee. Here, employee ID and project ID, by combining employee ID and project ID, we will get days. If we get employee ID gives days. Here this is the primary key. Then days, getting days, we should have employee ID and project ID. And if we define another functional dependency, employee ID gives days. For the same right hand side, we need only one left hand side, or we need only one attribute from left hand side. That means days partially depends the determinant. Here a determinant is employee ID and project ID. So here days completely or fully depends project ID and employee ID. But in the second case, days partially depends employee ID. Without getting project ID, we will get days. That means here partial dependency, here full dependency. Fully functional dependent and here partial dependency. Next is partial functional dependency. We already said that if a dependent partially depends a determinant, we can say that it's a partial functional dependency. We will avoid partial functional dependency in second normal form. For example, here employee ID, project ID, days and project cost are the attributes of the given table, and we already defined a functional dependency or primary key by using here we already defined a relation employee ID, project ID gives days. At the same time, here we will get project ID gives project cost, because here employee ID and project ID gives the primary key. Then if project ID gives project cost partially depends the primary key. That means only one part of the primary key is used in this functional dependency. So we can say that it's a partial functional dependency. Next one is decomposition rules in relation. Okay, decomposition is the process of decomposing a relation into smaller sub-relations, or we are decomposing or dividing an entire table into smaller tables. By decomposing, we have to apply some rules. Properties of decomposition. First one, lossless decomposition, which is the good decomposition, and next one is lossy decomposition, which is bad. And second property is dependency preservation. As we all know, lossless decomposition or good decomposition means when we are decomposing a table into smaller tables, we have to ensure that no information is lost during that process. Okay, the relation is said to be lossless decomposition if we apply natural join of all the decomposition should give the original relation. We can have an example. Here we have a table having 6 columns or 6 attributes: employee ID, employee name, employee age, employee city, department ID and department name. The table contains the information about employees and their departments. So this is a larger table and we have to decompose this table into two. For a student table or an employee table and a department table. If we are decomposing this larger table into two, a department table and an employee table, then we have to ensure that by combining that two tables, we should get all this information. So here we divided or decomposed like this. We will take 4 IDs: employee ID, employee name, employee age and employee city for employee table. And for department table also, we will have 3 columns or 3 attributes: department ID, department name and employee ID. Here employee ID, when we are looking into this table, we may thought that employee ID is unnecessary because this is the department ID table and department table, and which does not need the information of employee ID. But if we are not using employee ID, when we are combining this department table and employee table, we will lose some information because we cannot map the correct employee into correct department. This is known as lossy decomposition. In lossy decomposition, when we are decomposing a table into smaller tables, and after that if we are performing natural join or combining all the smaller tables, we will get or we will lose some information. For example, here the table having 6 attributes, we are dividing this table into department table and employee table in the like that previous case. Here the department table contains 2 attributes and employee table contains 4 attributes, 1, 2, 3, 4. But here in the second case, in the department table, we will have only 2 attributes, department ID and department name. In the previous case, we used additional one more, employee ID, but here we are not using employee ID. And if we when combining these 2 tables, the order may be changed because there is no common part between this department table and this employee table. So the order may be changed. That means some informations will be missed during combining. So this is known as lossy decomposition. Dependency preserving. Dependency preserving means when we are decomposing a relation into smaller relations, we have to ensure that all dependencies exist in the larger relation should be in smaller relations also. For example, we will have a relation R ABCD. That means we will have a relation R having 4 attributes ABCD and with functional dependency. That means that relation holds a functional dependency A gives BC. Then we are decomposing the table R into 2, R1 of ABC and R2 of AD. That means R1 having attribute ABC and R2 having AD. And in the main table, we will have one functional dependency A gives BC. By using R1, we can define the functional dependency A gives BC. That means the smaller relation R1 holds the functional dependency A gives BC. So, which preserves the functional dependency. If you are writing like this, R1 is AB, R2 is CD. Then we cannot preserve the functional dependency A gives BC because C is on another relation and AB is on another relation. That means which does not preserve the dependency. This is all about dependency and functional dependency. Thank you.